Hi, in this video, we want to take a look at Bayesian networks. All right, if you think about all the machine learning that you've learned in this program so far, there has always been one target variable. And so something about that is that not all situations do we have only one target variable. And the modeling there almost always is taking the point of view as a collection of variables lead to that one variable giving an output, the independent and dependent variable relationship. Well, graphical models, what they do, they allow us to have like all variables are predictor variables, all variables are target variables. Now, something about this is that if you go through and you look at Bayes' theorem, Bayes' theorem is a statement about about conditional probability. Right? With conditional probability, if A implies B, or probability of A given B is going to be proportional to the probability of B given A. All right, so let's think about this. Let's say that we look at conditional probability distribution of height given gender. Okay, think about height given gender. Well, given that they're male, they're going to be taller than the other population. Given that they're female, their height. All right. Well, in the independent dependent variable like framework, what we're saying is the height is dependent on gender. Well, what happens if I know like somebody is 7 feet tall? All right. Well, in that case, then really the independent dependent variable paradigm doesn't really work. But we can still look at conditional probability and go the other way. If I know that somebody is 7 feet tall, then it is more likely they're going to be a male because males are generally taller. Okay, so in this situation, when we talk about Bayesian networks, we're using the fact that if I have a dependent variable and I know its value, that can tell me about the predictors that led to it. And so when we build these graphical models, we really don't care about which ones are independent and which ones are dependent. What we care about is there a significant relation between the two variables? And what are they? And if I have other variables involved, is it important to consider these? Okay, so graphical models treat all variables as predictors and target variables. The Bayesian Learn package is really the only package that I've found anywhere that does structured learning algorithms. When you look at graphical models, almost everywhere, it's basically a subject matter expert says it's this relationship between the variables, and they make a model, and that it's kind of accepted as being correct. Well, what the Bayesian Learn package does, it lets the data speak for itself. It lets the data go and find what is the structure that is most likely given the observations that we have. Realistically, you need to have both subject matter knowledge and you have to have data to get the best models possible. I've used the Bayesian Learn package plenty of times, and where like subject matter experts have given me information, I try to use their information, I build a model, and I see, hey, that's a crap model because they have their belief and understanding really don't jive with what's going on in reality. Also, there have been times that I needed to use the subject matter knowledge to improve the model that I built. So when we do graphical models, it's probably the most important time that we strike that balance between data and prior knowledge. All right, so the Bayesian Learn package does a really good job when the data set is all factors. That's when it's most supported. Then after that would be with numeric variables. And now when it does numeric, it's assuming that we have a Gaussian distribution everywhere. So here, really what's going on is that it's assuming that we have like a classical linear regression model each time we look at a variable depending on others. It's always going from a classical regression point of view within the Bayesian Learn package. Now, theoretically, it could be any distribution, doesn't have to be Gaussian, but what's supported with this software is Gaussian bell curve. And when we have mixed data types. This package really does not support it very well, honestly. It has good features and it's very powerful. What I found is better is to convert all of your data to discrete variables and then run these models. I find that that's the best way to go. There are some functions within the package that will help you do that real easy peasy lemon squeezy. All right, so let's go ahead and start looking at an example. Let's look at the Hellfinder data set. Now this is a pretty, for what we've talked about, this is a pretty big data set. And we've got a whole bunch of variables. They're all factors. So we're looking at all discrete data. Yeah, this package greatly prefers, I think it only works with factors. I don't think it'll even take character strings. So we can just look through, see what's going on. Also, this package does not handle missing values very well, so you need to handle missing values before you start running the model. All right, so let's go ahead and let's build an actual model. So here I'm going to use the HC algorithm. Now, there's a whole bunch of different ways to build models within this package, but from a machine learning point of view, we really just care about the best model. We don't really care about how it was built. We just want to know which one is the best and how do I get it, not how is it built. So what I'm going to do, I'm going to take the HC function and I'm going to build the model, and then I'm going to drop this into graph_viz_plot. All right, so one thing you'll notice is that I'm not using the double colon notation in this. The Bayesian learn package really does not support the double colon notation very well. So if you look back at up the top, I loaded the entire package, and you can see that a function gets suppressed from the stats package because there's another function in Bayesian learn called sigma. So if I want to use that stats sigma function, I'm going to have to use double colon notation to call this up. This is one of the, so this is a, so this could lead to package confusion. So this is why I try to avoid loading packages if I can. Now, something about the Bayesian learn package is that it uses a different package for, or uses different packages for its visualizations. And so what's going on is it pulls it in. Well, if you don't actually load the package, it's not actually going to, it's not going to call these properly. So you have to actually, you have to go ahead and just load the package altogether if you're going to do the good visualizations. Also, these visualization packages are in the bio-based collection of packages. So what you have to do, you have to set your repository to allow packages from BioBase, and then you can load these packages. Until then, you won't be able to execute these. All right, so there's a whole bunch of variables. Here is my Bayesian network. All right, so what this is saying, let's just look at this bottom part right here. Here's a variable, here's a variable, and here's a variable. What this is saying is that if I know these two are the only ones, only two variables that directly influence this one variable. So if I have these, if I know the state, if I know the value of these two variables, then the rest of the data does not tell me about this one variable. So how do we interpret this? Well, notice I've got a variable here and a variable here that's leading to this. Let's say I don't know the state of this variable. Then what the Bayesian package is going to do, it's going to take knowledge from these two to figure out what's likely. Then it's going to take knowledge from here, and it's going to estimate what this will be. So this is a very powerful aspect that I can figure out what's likely to happen with just a few values already known. This is really cool. This is very worthwhile. So what we can do, if potentially, if I know this state, and I just plug it in, or then I can actually figure out what is most likely for all other nodes going along. How does it do this? Well, here there is a conditional probability relationship. Once I know this value, then using the modeled conditional probability, I can figure out what's likely here. All right, now that I know what's likely here, I can use that to figure out what's likely here. Okay. And once I have an estimate of what's likely here, I can do this. I can repeat on this one, and I can repeat on this one. Okay. So I'm like chaining down all the way to here. Now, something that is interesting, all of these arrows are kind of like, given this one, what's the probability of this? Given this one, what's the probability of this variable? Given this, what's the probability for this variable? It's figuring out the conditional probabilities all the way down. How this gets really powerful is that using Bayes' theorem, I've got a conditional probability going from here to here. By putting this information onto this one, it chains all the way down. And now I have an idea of what's likely here. If I have what's likely here using Bayes' theorem, I can go in reverse of the conditional probability relationship here and go back up. And this is called a V structure. You see how it causes it looks like a V? So by having understanding the distribution here tells me about the distribution here. Using Bayes' theorem, I can go in reverse and get the distribution of this node. And so with just a few known values, we can actually use the Bayesian package to figure out a lot of aspects of what's likely to happen in the entire state for our data. So this is actually makes a very good way to do imputation also, because if I'm imputing, I've got missing values, I can use what I have to figure out what's most likely. Pretty neat, pretty cool. All right, when we build these models, notice that we have a whole bunch of edges and arrows. All right, in this model, they're all arrows. So an arrow means that it's a conditional probability of this given that one. The one on the receiving end of the arrow is depending on the other one. In a situation where we have a relationship between two variables, but we don't have an independent-dependent relationship, then we're not going to have an arrow. It's just going to be an edge. Well, there's three types of mistakes that we can make. First and foremost, we can have an arrow where when there shouldn't be an arrow. We can have no arrow when we should have an arrow, or an edge, either way. And the other way is that the arrow is pointed in the wrong direction. There's three types of errors. Remember, in hypothesis testing, we only have two types of errors going in different directions. So each of these arrows, there is you can think of it as between each of these two variables, between every single pair of possible variables, there's a hypothesis test. Should there be an arrow there or not? Okay. And then we have type 1 errors, type 1 errors, type 2 errors, but we also have the arrow going in the wrong direction error. So we have to watch out for that. Arrow pointed in the wrong direction will be the most frequent error that you're going to encounter. So if you look at your model and you see that from subject matter knowledge, the arrow is pointed in the wrong direction, you can go, hey, I don't have faith in this, let's go ahead and switch it. And the Bayesian Learn package gives you operations to switch that up. Very nice. Now, something that you'll notice about this is that there's no cycles. This is called a directed acyclic graph. So there's only one route to get from one node to another node. So if I look through here, there's only one way for me to get from this node to that node. All right. Or there might be others, but it's not going to be a cycle going along the arrow. So you notice that I can go from here to there to there. I can go from here to there. But if I want to go back to this, I have to go against the arrow. If I follow the arrows, I can't make a loop. And when we have edges, that is, the connections are not directed, then this package will not let us have any loops going. All right, so when I look at this, I want to know how confident I am in each edge, in each direction of the arc. So what we're going to do, we're going to use the strength, we're going to use the arc strength package, sorry, arc strength function in this. So we just compute arc strength, and honestly, there's plenty of different ways to compute arc strength for each of the different types of modeling that you're doing. My opinion is that you should use the default method because they're pretty good. All right, so what I can do, I can actually print this now and take a look at what is the strength of each one, so I can see, hey, is there one that I don't feel confident about? Do I want to include some more? Do I want to eliminate a few? I find the best way to do it is to go ahead and use a strength plot. The thicker the arc, the thicker the edge, the more confident I am. So when I look through here, I see that this is a pretty thick arc. So that is the model is telling me that there's a very strong relationship here. When I look up here, that is thinner. It's a thinner arc. Therefore, I'm not as confident in that being the correct model. Now there's other plots, and these look really, really cool when you get these going. Unfortunately, in our markdown, these really don't look good. And in fact, when you have a lot of nodes like this data set does, it doesn't look good at all, honestly. What you have to do is either save it in like a PDF format and then like zoom in, and then it's really informative. So there are 3 types of special plots with using graphviz.chart. So I'm using graphviz.chart. I'm going to have a bar chart. Then I'm going to have a dot plot, and one more. So you can see this doesn't look very good, but if we were to zoom in, we'd see a much more interesting model. It gives us feedback. We can look at the conditional probabilities pretty nicely. We've got a dot plot. And this gives us further information, helps us visualize individually what are the marginal aspects of each node. And then we have a bar probability. And if you plot this on your machine with fewer variables, fewer nodes, it's going to look pretty good. All right, so one thing you'll notice is I just grabbed a model and I ran with it. I just picked the HC, the hill climber algorithm, and did it. Well, that's not a very machine learning point of view. Machine learning, we're trying to find the best model possible, and we're trying to let the data speak for itself. We want the data to lead to what the model is, not our prior choices. So what we're going to do, we're going to go through and we're going to let R take all of the possible different algorithms, and then we're going to run them, and then we're going to go through and pick the best one. All right, that sounds like a machine learning point of view, right? Okay, so here are the types of models that we can run through. And for our purposes, we really, when I'm doing machine learning, when I'm doing predictive analytics, I don't really care about what the algorithm does. I care, is it a good model, yes or no? So what we're going to do cross-validation. Now, I personally, in my opinion, I feel that two-fold cross-validation is the best way to go. Why do I feel that way? Well, let's think about let's think about all the different ways that we could do, we could validate our model. It's very common to go like 70-30 or 70-15-15, 60-20-20, stuff like that when it comes to the different types. I feel like cross-validation on two folds is the best way to go. Well, first of all, cross-validation, I'm using all of my data to see how good my model is. Okay. Well, now let's think about this for a moment. Let's say that I have 11 folds. I'm going to do 11-fold cross-validation. Okay, so I'm going to chop my data up into 11 groups. Then I'm going to pull one out. That's going to be my validation set, and I'm going to have the other 10 folds going. Well, with those other 10 folds, and I'm going to this becomes my training set. And I'm going to build my model. and I'm going to repeat, I'm going to go through each of these 11 folds get pulled out and are not part of the training set. Well, if I look at any two validation runs in this cross-validation run, then the data is 90% the same on each iteration. 90% the same. That means they're not independent. That means that I've got overlapping information. And frankly, I don't like it because we have a better alternative. If I do two-fold cross-validation, that means that when it's in the training set, it's not in the other training sets at all. There's no overlap between the training sets. So I choose two-fold cross-validation because each time I'm going to have independence between the set that are in the training observations each and every single time. All right, well, if you think about this, well, that's not really that many data points, right? You know, I'm only doing two-fold instead of 10. Well, what I do is I do this repeatedly. So I do, you know, independent sampling, you know, maybe 10 to 15 times, and then I do two-fold cross-validation each of those 10 to 15 times. And so then I've got things pretty separated out. And one of the advantages of this is I find it's easier to find outliers in your data when you do this. If you get some crazy errors, like you see that consistently one of your folds gives you bigger error than the other, then usually the one that has like a bizarre outlier is holding that fold. And I've used this in the past to find, hey, there was an outlier I missed. I need to go back. I need to do something about it, omit it, impute its values, change the weight. I find that this is a good way to go. Also, if I'm going with like 90% of my data for, you know, let's say I'm doing 10-fold cross-validation. If I'm using 90% of my data to compute a model, then that could take a while. Some of the model building algorithms take a long time. If I'm cutting it down to 50% of my data, that will be fast. So for the computations that take longer, when you have more observations, you can get more estimates of how good the model will be faster if you do two-fold cross-validation. And so I prefer it. I like it. I think it's a good way to go. I've never seen it used in literature though, but whatever. Don't listen to me if you don't like it. All right, so what we're gonna do, I'm gonna make a list. I'm gonna check it twice. So I'm gonna have lists of my cross-validation. And what we're gonna do, we're gonna go through each of these different types of models. I'm going to build the model. I'm going to build it, I'm gonna split my data in two twice. So I'm gonna take I'm gonna take my data, I'm gonna split it into two groups for each fold, and I'm gonna build a model. I'm gonna build a model on this and check how well it predicts here. I'm gonna build a model on this, check how well it predicts here. And then I'm going to do that all over again. So I'm gonna sample again. I'm gonna do a pseudo-random sampling and build a model, check its validity, build a model, check its validity. I'm gonna do that 2 times. Now, I only picked 2 on the number of runs just because it takes a long time. I usually put this to 10 when I'm actually building a model, but I think this is good for now. Now, you'll notice that I've got the try function going on in here. All right, so what's happening is that the models don't always work out when I try to call them. And, you know, I'll say, hey, take this model, run with it, and then, you know, build off of it. Sometimes it just doesn't work. Sometimes the model doesn't handle this type of data. So I just use the try function. I put it to silent, so I don't have to worry about any errors. It doesn't, you know, so I know that there's, it's not going to work out for some of them. I just don't even worry about it. I don't even look to see what doesn't work. What I do, I look to see what did work. And so the first one is the grow shrink algorithm. And we see average loss over the runs is 63. We have 2 runs. Here's the standard deviation of the loss. Okay, so notice I've got average loss of 63 and a 0.2 standard deviation. That means I've got pretty low standard deviation proportional to the average. So that means that we that we have more confidence in our measurements. And so here we have I, A, and B. And so we can see each of these, what the output is each and every time. All right, so now what I want to do, I want to extract the actual loss values from each of the folds. Okay. Unfortunately, in the Be and Learn package, it really does not support this feature very well. So what I want to do, I want to actually grab the values, and I want to be able to maybe make a histogram off of it. So personally, what I do when I do repeated cross-validation, I actually look at the histograms in addition to the mean and medians of my, my measurement of model quality. So this gets really ugly. I'm putting this in list format. I could honestly just pick my model just off of the output we've already looked at. But if you want to actually look at the histograms, you need to extract it more. So I go through, I create a list underscore mean, and I, because I'm extracting the mean of the mean of the loss from each of these. And here I get the results. So we can see that Taboo is the one with the least. And we can see that the gross shrink is the one that has the most. And so another run previously, Hill Climber came out as the best. This go around, Taboo came out as the best. These two algorithms are very close to each other in performance. Hill Climber is, I think, a little bit faster. So in the previous example, I ran the Hill Climber algorithm because it was the best one in the previous iteration before I generated this. Realize that anytime you do this random sampling aspect, you're going to get different values each time. The more runs that you have, the more stable it's going to be. All right, that's all I've got for you. I hope you're staying healthy. And take care.